Hello and welcome to Nikolai's genetics lessons, and here is a problem. There is a disease caused by the recessive allele. The parents are heterozygous. What is the probability that at most 2 out of the 4 children will have this disease? How many variants this family may have? Imagine that all 4 children can be healthy. So this is going to be one variant. 4 children would be healthy. So let's A would represent healthy child. And another variant would be that this family may have 3 healthy children and 1 child that is going to be unhealthy or would have this disease. Let's say that P would stand for this child. So 3 plus 1, 3 healthy and 1 unhealthy. So it's going to be P for unhealthy person. And another variant would be 2 children who is going to be healthy and 2 who is going to be unhealthy. So 2B. And another variant which is possible that 1 would be healthy child and 3 would be unhealthy. And the last variant would be when all 4 children would be unhealthy. And take a look. For example, when we have 4 healthy children, there is only one such variant. For example, first child would be healthy, second, third, and fourth. And as for this variant, we will have many more variants. For example, first child can be unhealthy, and 3 would be healthy children. But another variant also possible that first child would be healthy, then unhealthy, and 2 healthy in a row. Another variant would be that first 2 children would be healthy, then unhealthy child, and healthy. And the last variant would be when 3 children who is healthy in a row, and the last one would be unhealthy. As for the 2 children who is going to be healthy and 2 that is going to be unhealthy, we will have more variants. Take a look. For example, healthy, healthy, and 2 unhealthy. Another variant would be healthy and then unhealthy, healthy, and unhealthy. Another variant would be healthy, unhealthy, unhealthy, and healthy. Another combination would be unhealthy child, healthy, healthy, and unhealthy. Yet another variant would be unhealthy child, then healthy, unhealthy, and healthy child. And the last combination would be 2 unhealthy children in a row and then 2 healthy children. And here we have also 4 variants just like here. But here we have 3 healthy and 1 unhealthy. And this time we have only 1 healthy and 3 unhealthy. So what combinations are possible? That first child would be healthy and 3 in a row unhealthy. Another combination would be first unhealthy, healthy, unhealthy, unhealthy, then unhealthy, unhealthy, healthy, unhealthy, and the last combination would be 3 in a row unhealthy and the last one healthy. And another combination when 4 children would be unhealthy. Just like all 4 children would be healthy, we have only one such combination. We also have only one such combination when 4 children would be unhealthy. So first child, second, third, and fourth would be unhealthy. Now let's pay attention to our problem. What is the probability that at most 2 out of the 4 children have the disease? It doesn't mean that 2 out of 4 at most. So you have to pay attention at most. What does it mean? It can be also 1 child, so 3 healthy and 1 unhealthy. It can be 2 children, but it cannot be 3 unhealthy children we do not account this probability and this. So let me circle. That means that we only account for these 3 first columns, which represent where family has all 4 children, which is healthy, 1 child who is unhealthy, and 3 healthy, and at most where this family would have 2 children who is going to be affected with this genetic disorder and 2 who is going to be unaffected. And some of you may say that the probability is going to be, let's count how many combinations we have: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So some of you may say that the probability would be 1 plus 4, 5, plus 6 would be 11. So 11 out of 16. This is not true. Why? Take a look. We know that both parents are heterozygous for this genetic disorder. That means that father is heterozygous and mother is heterozygous. And if we build simple Punnett square, let's take a look what we are going to see. So probability for their children to have this genetic disorder is going to be 1 out of 4. So only 1 out of 4 probability, or 25%, would be probability that the child would be affected with this genetic disorder. So 1/4 and 3/4 is the probability that they would have a child who is going to be phenotypically normal or would be healthy. And probability to have 4 healthy children is not going to be the same as having 4 unhealthy children. Take a look. For example, probability to have a first child who is going to be healthy is 3 out of 4. Probability that the second child also going to be healthy is also 3/4. The same probability for the third child and the same probability for the fourth child. And for example, here, probability to have 4 children who is going to be affected with this genetic disorder is going to be 1/4 for the first child, 1/4 for the second, 1/4 for the third, and 1/4 for the fourth child. So what we are going to have here? We have to multiply all these independent probabilities, and what we are going to get: 3 times 3 would be 9, times 3 would be 27, times 3 is going to be 81. So 81 in numerator, and in denominator we have 4 times 4, 16, times 4, 64, times 4 is going to be 256. 256. And for example, here we are going to have 1 times 1 is going to be the same number. So in numerator we are going to have 1 over 256. Compare probability to have 4 healthy children and probability to have 4 children who is going to be affected with this genetic disorder. The difference is 81 times. This event is more probable than this event. Now let's count what is the probability to have 3 healthy children and 1 child who is going to be affected with this genetic disorder. Take a look. Here's our calculation. So probability that the first child would be affected with this genetic disorder is going to be 1/4, and that second child would be unaffected is going to be 3/4. 3/4 here and 3/4 here. If we multiply all these numbers, what we are going to get: 1 times 3 is 3, times 3 is going to be 9, times 3 is going to be 27. So 27 over 256. But take a look. We have 1, 2, 3, 4 such combinations. So we have to multiply by 4. So we are going to have 108 over 256. So this is probability to have one child who is going to be affected and 3 who is going to be unaffected. And as for this column, our calculations are going to be as follows. 3/4 is probability to have healthy child, 3/4 probability to have healthy child, 1/4 and 1/4 here. Again, we have to multiply all these numbers. And what we are going to have, 3 times 3 is going to be 9, times 1 times 1 is going to be 9. So we are going to have 9 in numerator and 256 in denominator. And again, we have 1, 2, 3, 4, 5, 6 different combinations. So times 6. And we are going to have 54 over 256. This is going to be a probability of having 2 children who is going to be affected and 2 who is going to be unaffected. And our final calculation is going to be to add all these 3 variants, so 1, 2nd, and 3rd, which represent this column, this, and this. So 81 plus 108 plus 54. So our last step in our calculations is going to be 81 over 256 plus 108 over 256 plus 54 over 256. And our final answer is going to be 243 over 256. And this is going to be our final answer. And if you need an answer in percentage form, you have to divide this number, numerator, by denominator. And the answer that you're going to get, you have to multiply by 100, and this is how you're going to get an answer in percent form. So this is going to be 0.949 times 100 would give us 94.9%. This is going to be a probability that this family would have at most 2 out of the 4 children that has this disease. This is probability. And hence, the probability that this family would have whether 3 or all 4 children who is going to be affected with this genetic disorder is going to be 100% minus this number, so 5.1%. And this is all for today. Thank you for your attention. Please subscribe for my new videos that I post almost every day. And see you in the next video. Goodbye.